Hello and welcome to this online video lecture about empirical and molecular formulas. This is going to be a two-part lecture. I'm going to split it in half, talking about empirical formulas first and molecular formulas second in another following lecture here. By the end of this lecture, you should understand what an empirical formula is and how to calculate one if you're given percent composition for a mystery compound. So let's get started. Sometimes in chemistry, you've got compounds that are similar because they're made of the same elements. And sometimes those compounds will be made even of the same ratios of those elements. So chemists have two formulas called empirical and molecular formulas to work with compounds that are similar like this. The one that I'm going to talk about first, empirical formulas, those are useful because oftentimes when chemists analyze a substance, they put it in a mass chromatograph or something. The substance will, the machine will spit back like the percent composition of that substance. And then using the percent composition, the chemist can calculate what's called an empirical formula. In other words, and they can basically figure out what elements are in that compound and what the whole number ratio of the elements to each other is. And that's what the empirical formula is called. The empirical formula is the smallest whole number ratio of elements in a compound to each other. So let me give you an example. There's a compound you probably have never heard of before. It's called diborane. Um, hold on a second. Get out of here. Diborane. So diborane's formula is B2H6. But that's not its empirical formula. That's actually its molecular formula, which we're going to talk about in the next lecture. Its empirical formula would be the smallest whole number ratios of these two elements to each other. Well, what is the ratio of these elements to each other right now? Well, it's an awful B. In other words, what's the ratio of boron to hydrogen in diborane? Well, it's 2 to 6. But most of you are math savvy enough by now to realize that that's not the smallest whole number ratio that you can have there. You can divide both those numbers by 2, and you can get a ratio of 1 to 3. So that means that the empirical formula, the formula with the smallest whole number ratio for diborane, would be BH3. 1B to 3 H's. That would be the empirical formula of diborane, the empirical formula. So what does this mean for you in this class? Well, for you in this class, you need to be able to take either percent composition for a compound or masses of elements in a compound, and you need to be able to calculate the empirical formula for that compound. So I'm going to run you through two examples right here, and we're going to look and see how this works. Let's say we did an analysis on some compound, and it spit back that it's got 32.38% sodium, and it's got 22.65% sulfur, and the final one is 44.99% oxygen. And we want to know what the empirical formula of this stuff is, of this compound. So here are the steps that you follow. First of all, percentages are useful in kind of telling us what's in the stuff, but if we want to calculate the empirical formula, we have to start talking about the actual elements and amounts of the elements that are in the compound. So we have to get out of percentages and into something that's a little bit more concrete. So the first thing we're going to do is convert all the percentages into masses, into grams. And the way that you do this is you assume that there's 100% of the compound. So some of you might be ahead of me here, but if you assume that there's 100 grams of the compound, all of these percentages just basically turn into masses. So where we had 32.38% of sodium, when you assume that there's 100 grams of it, that becomes 32.38 grams of sodium. Likewise with all the rest, the percentages just turn into masses when you assume you have 100 grams. So that's the first step, is to assume you have 100 grams and get those percentages into masses. Now the second step is we will actually want the whole number ratio of literally of the atoms of these elements to each other. And as you know, grams doesn't count the atoms. Grams is a measurement of the mass. So we have to get into a measurement that does count the atoms, and you should know by now that that measurement is moles. So the next step is convert all these masses into moles. So just a reminder of how you would do that. You've got 32.38 grams of sodium. You want to go from grams to moles. Then you need, if you've got grams of moles like this, you need the molar mass of sodium. So you look on the periodic table, which I of course have ready down here. I'll pop that right up and find sodium over here. And it looks like 22.99 is what we're going to use. So I'm going to put 22.99 grams. And when we do that, it looks like we're going to get about 1.4. Let's see, let me grab the calculator real fast. Get our handy dandy Windows calculator here. All right, so 32.38 divided by 22.99. Yeah, 1 point. So we'll use 1 point. Let's see, we want 4 sig figs. So 1.408 is what we're going to use. So 1.408. And then you do the same thing. You convert the other two to moles as well. So I'm just going to go ahead and pause the video for a second and do that real fast. Okay, I finished all these calculations. I calculated 0.7063 moles of sulfur and 2.812 moles of oxygen. Just a caution here, you're not dealing with elemental oxygen, you're not dealing with the diatomic elemental form. So the molar mass for this would just be the molar mass of one oxygen atom, so 16 grams per mole, not 32 here. Just a little heads up. So now what's the next step? Now we have basically molar amounts, and so now we're talking about particles. We're talking about, we can relate how many particles we have relative to each other. And so we're ready to actually start figuring out the ratio. So the final step here is to take these molar masses and divide them all by the smallest molar mass. And so by looking at these, our smallest molar mass is 0.7063, and that's sulfur. So our final step here is to divide the moles of sodium and the moles of oxygen by the moles of sulfur that we have, and we have 0.7063 moles of sulfur. So I'm going to take 1.408, and that's moles of sodium. I'm going to divide by 0.7063 moles of sulfur, and if you've got good mental math skills going on there, you can probably already see what that ratio is. But I'm going to go ahead and pull up the calculator here, and we can just be extra sure. So 1.408 divided by 0.7063. Okay, and now at first you might be kind of confused, and you might say, whoa, that is not a whole number. But look at how close it is to a whole number. 1.993 is ridiculously close to the whole number 2. And so that's what we're going to use. We're going to use that whole number 2 because we got so close to it. And that's what we're after. We're after whole numbers. So you have to, you have to recognize when you're really close to a whole number. And I think everybody recognizes that 1.99 is really close to 2. And then I just have to do that again with the oxygen. So I've got 2.812 moles of oxygen. I'm going to divide that by the 0.7063 moles of sulfur, and I'm going to try to get the ratio of those two. So again, if you've got good mental math skills, you might already be ahead of me here, but let me just go ahead and do it on the calculator. 2.812 divided by 0.7063, and we get 3.98. Oops, lost my calculator. Let me pull that back up. Let me get that fourth digit. 1. And again, that's not a whole number, but it's very close to a whole number, and that's the whole number we're going to use, and that's 4. So do you see when you do this division, you're almost never going to exactly get a whole number, but you will get very close to a whole number, and that's the whole number that you should use. Now you might be asking, well, what about the sulfur? What about the sulfur? Well, you'd basically divide the sulfur's number of moles by itself, and that's because that's the smallest number. That's why we divided these two by it. And so the sulfur would be 1. So this was for the sodium, right? This was the sodium's moles that we used up here. This was for the oxygen. This is the oxygen's moles that we used up here. The sulfur's whole number would be 1. So now we're ready to finally write our empirical formula. We have our whole number ratio, so now we just have to put it together. So this is where some chemistry skills come in. You need to know that the metal goes first, so sodium, and then how many of those? 2, right? And then you've got a sulfur and 4 oxygens. Does that sound familiar? Hopefully that's kind of scratching at the back of your head, because that's the polyatomic ion sulfate, SO4. And so you should know that it should be written that way. And so then we finally arrive at our empirical formula for this substance. It's Na2SO4, and that's your final answer. So that's how you calculate the empirical formula for a substance if you have percentages. So now you're not always given percentages, but actually that's a good thing, because sometimes a problem might just give you grams, masses. But that's actually a really good thing, because if you encounter a problem that just gives you masses, they've done some of your work for you. They're basically starting right here. So they start right here and move forward. They give you masses, right? These are masses right here. So you'd be starting right here, and the only thing that's different is you just don't have to do the assume I have 100 grams step. That's when you're given percentages to start. When you're given masses to start, you can just start with the masses, calculate the number of moles, divide those out to get smallest whole number ratio you can get, and then write out your empirical formula. So that pretty much wraps it up for empirical formulas. It's the smallest whole number ratio of the elements that are in a compound, and you can find that smallest whole number ratio if you're given percent composition or masses of the elements that are in a sample and of a mystery compound by turning those into moles and dividing them by the smallest amount of moles to get your smallest whole number ratio. Thank you for watching, and as always, if you have any questions, feel free to ask in class. Come back for part 2, and I'll talk to you about molecular formulas.